In this section, I'm going to add a few antennas into discussion. And for example, in this diagram, I have a periodical array of antenna arranged along x direction. And all the antennas have the same length. Also, the separation of the antenna is denoted by a distance d. And in this arrangement, we allow a phase difference for the currents driving antenna. For example, the phase difference between antenna 1 and antenna 2 can be c, and the phase difference between antenna 2 and antenna 0 can be 2 times c, and the driving phase of the current on antenna 3 can has a phase difference 3 c with respect to antenna 0. So finally, if you sum over all the radiation field from all the antennas in the far field, you're going to see that the antenna pattern is going to be multiplication of individual pattern function and the array factor A per C. So let's just spell out this array factor A of per C, which is the coherent sum of all the field from individual antennas. And between two antennas, you're going to see there's a phase difference of per C, which is given by this expression. And we have seen this expression before. This is basically the phase difference of the field from two adjacent antennas. And let's look into this expression and figure out which direction you're going to get strongest radiation, or which direction you're going to get no radiation. For example, let's confine our discussion to this xy plane where theta is equal to 90 degrees. So let's put the 90 degrees into the sine theta. So we simplify this phase difference per C to be beta d cosine phi plus c. And don't forget that the c is the phase difference between the driving currents for two adjacent antennas. So we'll be looking into the radiation pattern on the xy plane. Now let's try to look into the maximum radiation direction, which is consistent with this A per C equal to maximum. So we'll be looking into the value of phi that gives the maximum value of this array factor. And so if you try to look for the maxima from this array factor, then you're going to see that it will occur when per C equal to 0. So when per C equal to 0, this means that you put 0 on the left hand side, and then you can calculate this cosine phi equal to minus c divided by beta d. So if you have the angle phi angle equal to this value, you'll be looking into the direction where you have the maximum radiation intensity. Now, let's look at the direction. Well, we have defined the so-called broadside array and also end-fire array in the last session. For broadside array, you have the maximum radiation along 90 degrees and 270 degrees on the xy plane. So let's set this value into this expression. When you put 90 degrees or 270 degrees into this cosine phi function, you end up nothing on the left hand side. So this means that if you want to have a broadside radiation, you have to set this phase difference of the current equal to 0. Therefore, you have such a broadside radiation along 90 degrees and 270 degrees. And sometimes we want to know the directivity of the antenna, and that is related to the beam width. If you have a narrow beam width, this means that this antenna is going to radiate energy into a small angular cone. So we want to figure out the beam width of this radiation pattern. and the easiest is to plot it in the XY coordinate system. And in the vertical axis, we have the intensity of the radiation, and the horizontal axis is going to tell you the angle where you have the radiation. So the width of this beam is going to be the distance between the nulls of those radiation lobes. So let's look into the nulls of this array factor. So set this A of C equal to 0, and you're going to see that this will happen when this sign n per c over 2 is equal to 0. Because when this is 0, then you have the 0 for this A of C. So you write down this expression consistent with the sign n per c divided by 2 equal to 0. So the argument of this sine function will have to be equal to n per c equal to plus minus 2n pi, where n is the integer. And the separation of the two nulls is going to be equal to 2 pi. If you take this, the delta per c n equal to plus minus 2 pi, you'll be able to calculate the width of this beam, which is given by this 2 pi divided by n. And from this expression, you see that the beam width is closely related to the number of antennas in the system. If we have more antennas in the system, the beam width can be narrower because the width is the 2 pi divided by n. So on this page, let's look into this effect of n. Suppose now I design an antenna array to radiate as a broadside array. Then from the last page, I want to set this c equal to 0. And so if I plot the pattern function as a multiplication of the f of theta phi multiplying with the array factor, then for n equal to 2 on the xy plane, I have such an antenna pattern. But if you plot that with n equal to 4, you start to see the beam width gets narrowed down. Now, if I plot n equal to 6, then I have even narrower beam width. So if you want to have a good directivity for your antenna array, you want to increase the number of the antennas in the system. On the other hand, we can also design such an array antenna to be an end-fire array. By definition, if you have an end-fire array, you have the maximum radiation intensity along phi equal to 0 direction. Now, let's find out the condition for this end-fire array. Well, again, let's just look into the radiation pattern on the xy plane where theta is equal to 90 degrees. So you set theta equal to 90 degrees into this expression, and then specify this the A of per c equal to maximum. So we are looking into the maximum radiation intensity direction, where this per c is equal to 0. So you have a condition just like before. You have cosine phi 0 equal to the minus c divided by beta d, and this phi 0 is the angular direction where you have the maximum radiation intensity. Now, for end-fire array, you have the maximum radiation along phi 0 equal to 0 direction. So let's set this condition into this expression. Then this expression is going to give you cosine 0 equal to 1. So you have a condition for this c phase, which is a phase between the driving currents for adjacent antennas. So you have this phase equal to minus beta d, and this beta d is going to be determined from the ratio of the separation of the adjacent antenna to the wavelength. So now let's look into the nulls of this array factor because we want to know the width of this antenna pattern because this width is going to tell you within what angle the signal can be transmitted. So again, set the array factor equal to 0 so that you can find the null locations in terms of the per-C and then in terms of phi. So if you set this array factor equal to 0, then you'll be looking into the solution for sine n per-C divided by 2 equal to 0. And then you get this n per-C equal to plus or minus 2 pi n, and n again is the integers. So with this, just like before, you can calculate the width of the main lobe to be equal to 2 pi divided by n. So again, this antenna number of the antennas in the system determine the width of this radiation lobe. So on this page, we can also design an n-file array and start to see how n is going to affect the radiation beam width. For this design, we set the separation of two adjacent antennas to be quarter wavelengths, and then this c is set to be equal to minus pi over 2. This means that the separation of the two antennas is equal to quarter wavelengths. For n equal to 10, you can plot this antenna pattern. Then if you increase the number of antennas to 30, then you start to see the width become narrower. And if you continue to increase the number of antennas to 50, then the beam width is going to be even narrower. So this gives you a way to design the radiation intensity along different angle. For example, if you can dynamically change the angle, the phase angle of this c over time, then you can design an antenna array which can scan over different angles so that you don't have to rotate your antenna when you want to look into some signal along some direction. Basically, you can just electronically scan the antenna pattern by varying the phase of the driving current. So in this session, we talk about antenna array， 也就是阵列天线。这个阵列天线呢，我们讨论到的是周期的阵列天线。这个周期阵列天线呢，每个天线中间距离是一样的，然后每个天线的这个大小是一样，电流也是一样。但是呢，我们允许一个这个相位的差异在每个天线里头。这个相位的差异呢，会很容易的可以让你设计，就是你的这个讯号要扫的方向在哪个方向上头。那这个整个的 antenna pattern 呢，也是一样，两项的相乘，一个是单一的 pattern function， 叫做 element factor， 乘上所谓的 array factor。这个 array factor 呢，是来自所有的天线产生了场的原场的干涉的一个结果。那因为你可以控制这个电流的这个个别电流的相位，所以呢，你的 antenna pattern 辐射的方向呢，也可以用电子的方法来扫出各个方向出来。那这就是这个阵列天线一个很重要一个特性，也就是你在一般的这个船舰或者是雷达站呢，有时候会看到雷达这个天线呢是在旋转的，但是呢，你如果有个阵列天线的话呢，那你可以用电子的方法来扫出不同方向的这个辐射的这个强度，或者是接收不同方向的这个讯号。那这个在很多应用里头，特定方向的这个讯号的传输相当重要。那这个是由这个天线的 directivity 来决定，也就是你的 beam width 如果越窄的话，你的方向的选择呢越精准。那这个呢跟你的number of antennas in the array 有很大的关系。所以呢，你如果有很多的这个天线在里头的话，那这个 directivity 呢通常是会更好。那这个是这个小节里头所要介绍的重点。谢谢。